This is not working yet. I've had this for 5 years.
Did you guys ever take your credential?
5 years is an
What
exaggeration.
happened was a lot of police downstairs with people and the others inside the closet. And it's past her, so. She's on the phone. I mean, we figured that's what it was. You have just been escaped on accident before, like you off in the corner. You're like, is there any chance that we just overrun? Not the way you're sitting as well.
Excuse me. Good morning, everybody. Going to continue with the 5.2 that deals with the definite integral. I wrote down the definition yesterday and was pointing out a few things about it. So there's a few more things to point out, but I wrote down the definition again. But this whole symbol represents the definite integral. And it is a calculation. It's a number. And the number is calculated by taking function values at the different, in the different rectangles, multiplying them by the width, adding them all up, and then evaluating the limit as the number of rectangles approaches infinity. And the delta x is the width of the rectangle, which has the formula b minus a, where b and a, those are the upper and lower limits, or starting and ending points, and you divide it by n, the number of rectangles. So, note number 4. Pointing out a few things about this. It says, although we have defined this definite integral by dividing the interval a to b into subintervals of equal width, that doesn't necessarily have to be the case. There are situations in which it is advantageous to work with subintervals of unequal width. So it's kind of wordy there, but it's just saying this definition, this delta x, is the width of the rectangles. And it's the same for every single one. If we've got this function and we're calculating this definite integral from a to b, we construct these approximating rectangles. And I didn't do a great job, but the idea is each one of these has the same width. Each one of them has a width of delta x. Every single one of them. Which, again, has the formula b minus a over n. Take the endpoint minus the beginning, divided by the number of rectangles. But what this is saying here is that doesn't necessarily have to be the case. These really don't have to be the same width. You can have some that are wider, some that are more narrow, and everything would still work. You'd get the same number. You could have a real wide rectangle, maybe some narrow ones, maybe a medium one there, and a few more there. But the width are not the same, yes?
That be used when you have like a non-consistent slope or something? Like, when would you change it then?
It would sometimes be useful in the, but yes, I see what you're saying. Yes, exactly. Like what I did here is at the beginning, it was kind of linear function here, and then it started curving more sharply. So you can approximate the area really well with a wide rectangle, but then when it starts curving sharply, narrow ones will give you a better approximation. So sometimes it can just make computations easier instead of, splitting this up into 4 rectangles, just one big one, will give you a good approximation. So as the slope changes, then using different sizes may help. If that's the case, then there's slightly different notation. We'd call this delta x1, because it's the width of the first rectangle. We'd call this delta x2, delta x3, delta x4, delta x5, delta x6, delta x7, and so on. Because they're not necessarily the same. Up here, I can just use delta x because it's the same. Same delta x, same width for every single one. But here, not necessarily the same. It can vary from one to the other. But one thing that is very important, if they have different widths, we still need the limit as the number of rectangles approach infinity for all these rectangles to get narrower and narrower. It could be the case, if I didn't specify that we have these rectangles and this first rectangle just stays this width, and then the number of rectangles over here approaches infinity. And that would appear to match the definition, number of rectangles approaches infinity, but this one is just staying the same size. You need all of them, even the wide ones, as you construct more rectangles to get narrower and narrower. The width of every single one of them has to approach 0. So if this is the case, if you construct rectangles that don't have equal width, it has a slightly different notation. So it's if subintervals have width delta x1, delta x2, delta x3, and so on. The last one, delta x sub n. We have to ensure that all of these widths approach 0. In the limiting process. This happens if the largest width which they label maximum, MAX max, delta X sub I. So this just represents the maximum width of those rectangles approaches 0. So in the case So in this case, the definition of a definite interval becomes a definite interval is the limit as a maximum delta X sub I approaches 0 of the sum I equals 1 to n f of xi star times delta xi. So instead of saying the limit as n approaches infinity, we have to say the limit as the width of the maximum rectangle approaches 0. But really, the implication there is too that the number of rectangles approaches infinity. For that to happen, all of these, as you increase the number of rectangles, has to get smaller and smaller, all of them. So we still get an infinite number of rectangles, but the width of each single one is getting smaller and smaller. It's approaching 0. So with this definition, it's saying the width of the rectangles can be anything really, as long as it approaches 0. And the x value in each rectangle can be anything. It doesn't necessarily have to be the left side or the right side. It could be right in the middle. It could be somewhere maybe towards the left or right. It could be any point in there. But the idea is, of course, that the x value, the x sub I star, is trapped in here. And as the widths get smaller and smaller, you're going to get a better approximation of the area, or the sum of those approximated rectangles. Note 5. We have defined the definite interval for an integrable function. I want to pause for a second. Of course, there's a lot more here, but back here yesterday when I talked about this definition of the definite interval, it said the definite interval is a number. We calculate it by taking the limit as the number of rectangles approaches infinity. And if you can do this calculation, then that function f is said to be integrable. But that doesn't necessarily imply that all functions are integrable. And it actually doesn't even imply that any functions are integrable. It just says if we can do this, then that function's integrable. But anyway, this part here is telling us that most functions are. But it says not all are. says we have to find the definite integral for an integrable function. So it says if we can do it, it's integrable, we can do it. But not all functions are integrable. The following theorem shows that most commonly occurring functions are in fact integrable. Theorem says if f is continuous on AB, or if f has only a finite number of jump discontinuities, then f is integral. That is the definite integral exists. There's still a little bit more to add to this, but I just want to pause for a second and point out some stuff. It says if it's a continuous function, then we can do this. It also says if it has a finite number of jump discontinuities. So it doesn't even have to be continuous. It has a finite number. So not an infinite number of jump discontinuities, but a finite number of jump discontinuities. Then we can do this. So with this, would that exist? Of course, we haven't talked about how to actually do it yet with that definition, but we can answer the question, does that exist? I've got the integral from 0 to 1 of cosine. So does it fall into that category where it's continuous or just have a finite number of jump discontinuities? Yeah, cosine's continuous. Cosine just looks like that. And here we're just going 0 to 1. So let's see. I guess I'll be right about there. Definitely continuous from 0 to 1. So yes, would. So it's continuous. Would this exist? -2 to +2 absolute value of x. that exists. Absolute value looks like this. It's just a V. I'm going from -2 to +2. So would I be able to calculate that, or does it exist? Is it continuous? Yeah, it's continuous. Yeah, so it does exist. By the way, as a side note, does the derivative of absolute value of x exist everywhere in the interval -2 to 2? We just said it's integrable because it's continuous. But does the derivative exist everywhere? The answer is no, because of that point right there. Now it'd be differentiable everywhere else, but not right there at x equals 0, because of that sharp point. If you just think about tangent lines, there's not a well-defined tangent line there at that point. Anywhere else there is. The tangent line would be right on top of the line. Over here, right on top of it. But right here, no well-defined tangent line. Which way does it go? So the answer to this is no. The derivative would exist everywhere except at 0. But what I'm trying to point out is it's actually easier to be integrable than it is to be differentiable. Less restrictions. What about, I don't know, -3.5 to 2.5 of the greatest integer function? I don't know. I don't think we've talked about that greatest integer function in this class. We have? Yeah, okay. It's just saying if you plug in a number there, find the biggest integer that's less than or equal to the number you plug in. Like the greatest integer function applied to 3.5. You're trying to find the biggest number that's an integer that's less than or equal to 3.5, so it'll be 3. I apply it to 3.7, still 3. Biggest integer that's less than or equal to 3.7 is 3. So on and so forth. The graph of that looks like a staircase, kind of. Because you can see here from 3 all the way up to like 3.9 or 3.99, the answer is always going to be 3. Likewise, from 2 to 2.9, it's always going to be 2, so on and so forth. So you end up with a graph that looks like this. And it has these steps. They go forever in both directions. So if I'm interested in -3.5, -3.5 to 2.5. From there to there, would I be able to, actually I should phrase that differently. Does this definite integral exist? No. This theorem says it exists if the function is continuous. That's not continuous, obviously. Or has a finite number of jump discontinuities. It does have a finite number of jump discontinuities in this interval -3.5 to 2.5. There's a jump here, 1, 2, 3, 4, 5, 6. There's 6 jumps. So there is a finite number of discontinuities.
We're gonna say like negative infinity to infinity, then it wouldn't exist.
Yep. Well, I should say that it would then imply that we should, if it went on from negative infinity to positive infinity, there would be an infinite number of jump discontinuities, and that theorem then says we can't make a conclusion. Would be the best thing to say. Maybe it still is integrable, maybe not. But this just tells us some of them that are, which actually includes a big list.
Work the same way.
Tangent? Exactly. Let's look at tangent. Is tangent integrable? If I do negative pi over 4 to positive pi over 4 of tangent, would that exist? Tangent, negative pi over 2, positive pi over 2, has this graph that looks like this, and it repeats over and over again. So if I'm looking at negative pi over 4 to positive pi over 4, from here to here, would that exist? Yeah, because it's continuous to that in that interval. So yes, it would. What if I made this bigger though? I want to change that to pi. Change it up a little bit to pi. Negative pi over 4 to pi, tangent of x dx. Does that exist? So negative pi over 2, positive pi over 2, pi. We've got this, another one there. This time negative pi over 4 to positive pi. So that's here to here. So that would be this together with all of this one. Does that exist? No. Again, what I was trying to say there, this tells us when things are integrable. Doesn't necessarily tell us when things aren't. So really, we can never say, no, it's not. It does not exist. The best we can do is say, this theorem doesn't prove it does exist. We don't know for sure. Because this theorem just says if it's continuous or has a finite number of jump discontinuities, then it definitely exists. If it doesn't satisfy that condition, that it's not continuous or does not have a finite number of jump discontinuities, then we can't make a conclusion. So what about this one? Can we? So the choices are, it does exist by that theorem, or we don't know. We can't make a conclusion by that theorem. Can't make a conclusion. Because there's a discontinuity, but it's not a traditional jump discontinuity. It's going to infinity. So it's not just jumping from one point to another. It is, in a way, jumping from positive infinity to negative infinity, but that's not what a jump discontinuity is. It jumps from one finite number to another. So here, we don't know. Cannot make a conclusion. I don't know. Do you think it does, though? Just trying to maybe think about your intuition. Do you think it would exist? It's a tough question, though. you think about it as being those approximating rectangles, it seems like you might be able to construct them, might be able to do the calculation. It might exist. But the truth is, you can have two functions that are extremely similar and just differ by just a little bit. And one would be integrable and one would not. Anyway, I shouldn't have erased this yet because there was more to note 5. So continuation of note 5. So continuing note 5. If f is integrable on a V, so if we know that the definite interval does exist, then we limit in the definition exists and gives the same value no matter how we choose the sample points x sub I star. The definition said a to b of x dx is equal to the limit as n approaches infinity, sum I equals 1 to n, f of x of I star delta x. This x of I star is any x value in the ith interval. If limit or this interval exists, it's going to give us a number, and it doesn't matter how we calculate this exactly, because the x of I star can be any x value in there. It's always going to give us the same thing if it exists. So if that's the case, we should make it easy on ourselves and pick a particular x of I star so that the calculation won't be random like this, because it's any random number really in the ith interval. So let's pick the right endpoints and make it easy. So to simplify the calculation, of the integral, we often take the sample point to be the right input. Still a little bit more to add in it. Let me draw the picture again. A to B, got these rectangles. This beginning point, we call it x0. This x value here at the end of the first rectangle, called x1. It's in between the first and second. x2, x3, all the way to the end. Call that x n. The x of I star could be any x value in each rectangle. So x1 star is any x value in there, in that first rectangle. Maybe it's right in the middle. I kind of drew an arrow there like it's right in the middle, but it could be anywhere. And it could even vary from rectangle to rectangle. This one maybe that's x2 star, a little closer to the left side. As long as it's in there somewhere, it's fine. x3 star all the way to xn star. But what this is saying is instead of just having any randomly selected x value in there, since the no matter what, just pick the right values. That way we know exactly what they are. It's not vary from one to the other. So instead of x1 star, we're going to pick the right side, which would be x1. For the second rectangle, instead of x2 star, instead of just some random x value in there, pick the right side, x2. And so on and so forth. Instead of some random x value in the third rectangle, pick the right side. So instead of a random x3 star, pick the x3. Then x by star is picked to be the x sub I. So this looks like a kind of a trivial equation, but it's saying instead of a random x value in the interval, we're picking the specific x value that is the right side. And the definition of an integral simplifies limit n approaches infinity. Sum I equals 1 to n f of x sub I delta x, where delta x equals b minus a over n. And also, since these are the right endpoints, we could specify a formula for them. X sub I equals a plus I delta x. So it almost seems like I didn't really do much at all. Just left off the star. That's really the only difference in the way I wrote this and the generic definition. But again, the idea is this is much easier to calculate if we had to calculate it in practice. Because this, again, could be any random number in there. Instead of any random number, we're saying we're going to fix it at the right side. And we can calculate that. Because if we got A and B, those are numbers. We know how many reckon. We could calculate the x1, the x2, x3. We could take those numbers and plug them into the formula for the function. So we could calculate this for each one individually. We could multiply by the delta x because we could calculate that, then add them all up, see what we get, and then let the number of rectangles approach infinity and see what that length is. So they're going to have you do that with some problems, but most of them are kind of approximations and rewriting the definite integral as the limit of a Riemann sum, so on and so forth. Problem 1 in particular is exactly the same as stuff we saw in 5.1. number 1 says, consider the given function f of x equals 1 minus 1 half x. Evaluate the Riemann sum for 2 less than or equal to x less than or equal to 14 with 6 sub-intervals and they say taking the sample points to be left inputs. So we had problems like this in the previous section. But in the previous section, we were always calling it area. We constructed rectangles. So that's what we're going to do here. 6 rectangles. Except the only difference is we're not calling it area because this function is not necessarily positive. So it's not always above the x-axis. So it's kind of awkward to talk about area below the function down to the x-axis if it's not always above the x-axis. So instead of calling it area, we call it Riemann sum. Again, Riemann sum is just this part of the definition of definite interval. This part, before we take the limit, it's called the Riemann sum. So we need to do the sum for 6 rectangles from 2 to 14. So we need to evaluate the function with the sample endpoints, and they say use the left endpoints. So we need to do basically length times width for 6 rectangles. They don't have a picture drawn. And it's definitely possible to do this problem without a picture. But I always find it easier to draw a picture. And what I mean is draw the graph of this. Draw the rectangles from 2 to 14. See what it looks like. What time is it? 44. All right, so what type of graph is this? It's a line. It has a y-intercept of 1, has a slope of -1/2, has an x-intercept of 2, because if x were 2, I'd have 1/2 times 2, 1, 1 minus 1 give me 0. So y-intercept of 1, x-intercept of 2. Look like that. The interval we're interested in is 2 to 14. 2, 14. And I want 6 of them. So what does the width have to be? Well, the width, delta x, has this formula v minus a over n. So it's 14 minus 2 over 6. We're doing 6 rectangles. So that's 12 over 6, which is 2. So the width is 2. For each individual one. So I need one rectangle. I'm starting at 2 to go to 4. Then I need the next one 4 to 6, 6 to 8, and so on. The last one's going to be 12 to 14. I'm going to actually do it first because the first one's a little bit confusing maybe, but it's not as confusing at the end. When I draw the rectangle, they say the left side of the rectangle needs to match up with the function. They're saying use the left endpoints as the sample points. So when I draw the rectangle down, it's the left side that needs to intersect with the function. So it looked like that. You just working my way backwards. The left side needs to match up. Left side. Same all the way through here. And then this first one, I left it to last because it's kind of confusing because it's the left side that needs to match up and it's right on 0. So in a way, there's no rectangle there at all. Or it could say its height is 0. So there still are 6 subintervals. It's just that rectangle has no area. 1, 2, 3, 4, 5, 6. And really, it is still just can be interpreted as the area, even though it's below the x-axis. We just are going to get a negative when it's below. But anyway, what this formula says is I need to take the function value at the left endpoint times the width for each one of these. So the left endpoints I equals 1, 2, 3 up to 6. We're using 6 rectangles. The x sub 1 star is the left side, which we call x0, which corresponds to the a, which is 2. And then I need the function value. F of 2 is 1 minus 1/2 times 2, which is 0. For the second rectangle, the x value there is 4. And I'm running out of time, so I'm going to do this quickly. F of 4 is -1. For the third one, the x value is 6. The left side of that third rectangle is 6. Get -2. Fourth one, the x value they want me to use is on the left side there, 8. F of 8, -3. Fifth one, it's 10. F of 10. -4. And then the last one, the x value they want me to use is on the left side there, so it's 12. So let's make it 5. Now I need to take each one of these times the delta x, which is 2. I need to take that function value times the delta x. So I got 0 times 2 plus -1 times 2 plus -2 times 2, -3 times 2, -4 times 2, -5 times 2, which is 0, -2, -4, -6, -8, -10, which is 10, 20, 30, -30. So I get -30. So So very similar to what we did last time. Of course, though, we're calling it 3 months on the area. In fact, it's a negative number, so it doesn't make sense. But it can still be interpreted as area, or the negative of the area. It is still actually the area of these rectangles added together, just with a negative sign. Anyway, that's all for today. Tomorrow, do some more of these. Finish it up. Have a great rest of your day. See you all tomorrow.